All right, let's just do a little bit of a review and recap here, just to kind of make ourselves on the right page. So in the activity that we were looking at on Tuesday, they gave us a very detailed kind of flow chart that looked a lot like this. All we're going to do here is we're just going to kind of make a simplified version to help us to very quickly categorize based upon a few simple kinds of questions. So up here at the top, we're going to start with matter. We know that matter is everything. It is in everything. It is part of everything. And the first question that we can ask about matter is, how many substances are present? If the answer is 1, then we are dealing with a pure substance. If the answer is 2 or more, then we know we are dealing with a mixture. So right away, we can separate matter into 2 broad categories based upon that first question. How many substances are there in whatever it is that we are looking at? Within a pure substance, we can ask another question. How many types of atoms are there? If the answer is 1, we know that we're dealing with an element. Now we know from the activity on Tuesday, that element can appear in a couple of different forms. It could appear as individual atoms. It could appear as an array of atoms, like we saw in the metal sample. It could appear as individual molecules where we've got multiple atoms of the same kind bonded together in some kind of way. Lots of different ways of showing it, but if there's only one type of atom there, it's an element. If there are 2 or more, then we are dealing with a compound. And under compound, we're going to write the words fixed ratio. And the reason we're going to do that is because we have to understand that what makes a compound different from a mixture is that the substances, the atoms that make up that compound exist in that fixed ratio. If I'm looking at water, water is always going to be 2 hydrogens and 1 oxygen. If I'm looking at glucose, it's always going to be 6 carbons, 12 hydrogens, and 6 oxygens. I change that ratio in any kind of way, I'm no longer dealing with that substance. Whereas with a mixture, there is no set ratio for that mixture. The question that we ask about mixtures to help set them apart is about their appearance. If their appearance is uniform, meaning we can't tell one component from the others, they all look the same, then we call it homogeneous. For a lack of better term, disuniform, or just kind of varied, we're looking at a heterogeneous mixture there. So the flow chart that we saw in the activity on Tuesday had a lot more information in it. It defined each of these terms. It talked about how we can tell one apart from another. It talked about the idea of physical changes and chemical changes. It had all of that. But if it comes down to just classifying, we can classify just based on these simple questions. Any questions for me? All right, so based on that, let's just quickly go through a couple of study questions and just make sure that we're on the same page here. Okay, if I have pasta and tomato sauce, would that be a pure substance or a mixture? Definitely a mixture. And heterogeneous one at that. Aluminum foil. It's a pure substance. We can pretty safely assume that aluminum foil is all aluminum. Helium. Also a pure substance. This is elemental. Air. Also a mixture. And this one would be an example of a homogeneous mixture. I can look through the air here and, unless there are colored gases in there, I'm not going to be able to distinguish one gas from another. Okay. Here are four mixtures. Are they homogeneous or heterogeneous? Hot fudge sundae. Heterogeneous. Shampoo. Homogeneous. Sugar water. Okay. Dissolved sugar water. Homogeneous. Okay. I get what you're coming from. You've got iced tea and you're trying desperately to stir some sugar into cold iced tea. You might as well stir it forever. That would be heterogeneous. But assuming that you can get it to dissolve, it becomes homogeneous. Peach pie, heterogeneous. Okay. We touched on this at the kind of the middle point of Tuesday. Let's see what we remember about phases. This phase has a definite volume, but takes the shape of its container. Liquid, absolutely. The particles of this phase are moving rapidly. Gas, definitely. The particles of this phase fill their entire volume of the container. Also gas. These particles have a fixed arrangement. Solid, that's why they have a defined shape. The particles are close together but moving randomly. Liquid. That's why liquids don't have a defined shape. So the difference between D and E there is that movement of the particles. That little bit of movement allows the shape to be able to change in a liquid, but not in a solid. All right. One last thing that we did not touch on, just want to kind of make sure that we have it, are the idea of physical properties and chemical properties. Now, physical and chemical properties are kind of easy to confuse. So we want to just take a minute here and just make sure that we define them appropriately and know when they're used. In general, the main difference between physical and chemical properties are that chemical properties describe chemical reactions. And what I mean by that is they describe what happens, whether a reaction happens. So we're talking about properties like flammability, corrodability, oxidizing nature, things that are directly involved with actual chemical reactions taking place, and whether those reactions will take place for that kind of a substance. Physical properties, on the other hand, are the describable properties, things that we can easily observe without actually changing the object itself. I can pick up this pen and tell you that it is a blue pen, and I won't have to do any chemical reactions to it to tell you that it is blue. I can also tell you that it is a solid. I can tell you that it has a certain density. So all of those things that I'm describing, those are physical properties. They're the things that are easily described, and we don't really have to do anything other than just watch them. And so here are just some examples of physical properties related to copper. We can look at its color. We can describe it as it's being shiny. We can talk about its conductivity. We can talk about, here's its current phase at room temperature as a solid. But if we raise the temperature up to 1083 Celsius, it melts. If we raise it up to 2567, it starts to boil. Closely related to physical properties are the ideas of physical change. Now, physical changes are going to be observable changes in a substance, but we're not going to change anything from a compositional standpoint. So these are all things that we can observe, things that we will note as a change, but they don't change the actual chemistry of that substance. I can take this tissue and this one, that one, I can rip them into pieces. I am changing the structure of these pieces of paper, but I'm not actually changing anything compositionally. If I look at the structure cellularly, the structure chemically of what this paper looks like, I'm going to find that all of the carbons and hydrogens and oxygens are all exactly in the same places they were beforehand, put out in the exact same ratio to make the same compounds that were there all the whole time. That's a physical change. If I have a substance that goes through a phase change, solid to liquid, liquid to gas, gas to solid, those are all physical changes as well, because again, all that is changing is the phase of matter. Nothing is changing chemically about the substance. Sean.
Okay, so that's the case. Still there.
Okay, but when you burn something, if I were to burn this paper, right now this paper is mostly cellulose. It's a big, long, starchy sugar compound. As soon as I introduce flame to this, I'm introducing more oxygen. I'm now no longer getting cellulose. That cellulose is converting into carbon dioxide and water vapor and some carbon ash. I've changed the substance. It's no longer cellulose. Now it's carbon dioxide, and water. So from that standpoint, yes, there are some physical changes of state, but they come as the result of a chemical reaction, not just a random change from cellulose in the solid phase to cellulose in the gas phase. And so that's where it gets complicated and tricky sometimes, is trying to put your head around, okay, I noticed this happening. Is it happening because the composition of the stuff is changing? Or is it happening because the physical appearance is just changing and structurally everything's the same? So some common examples of those things like boiling water, dissolving something in water, taking a copper block and drawing it into wires for electrical wiring, cutting up a piece of paper into many tiny little pieces, grinding pepper or salt and putting it on your food. The act of cutting it and grinding it doesn't change the composition itself. Now, when you eat it, that's when the change actually takes place from a chemical standpoint. When we talk about chemical properties, again, we're talking about what happens when a substance goes into a chemical reaction situation. A chemical property would be, will this paper burn?
There's an exception to that. I guess.
I'm listening.
Onions. Would that-
No.
Because whatever it is, isn't present until it's
Okay, so you're talking about if you cut an onion and it releases that vapor that causes your eyes to sting. Okay, that compound was always in the onion. It was just trapped inside of the cellular structure of the onion. When you cut the onion, you are basically breaking the jail cell that the sulfur compound is held in. Now it gets released as vapor. It hasn't changed chemically. It's just been released. It'd be the same thing as if I were holding a canister that had natural gas in it, and it was closed. And we all know natural gas has an odor to it because we add something to it to make it smell. Well, if I had that glass canister and I dropped it on the ground and it broke, the gas inside of the canister didn't change. It's just no longer trapped. It's now open, and you can start to smell it because it's now open. It's the same thing with the onions. That gas is trapped in a cellular prison. And when you cut the onion, you have broken the walls of that cellular prison. Now it's able to come out. Now you're able to experience it. But prior to that, it was trapped inside of the onion skin and inside of the actual cells of the onion itself. So that's still a physical process. We haven't done anything chemically to make that happen. Everything's been done physically. Chemically, chemical properties, chemical changes, we're talking about the stuff itself has to change. The stuff itself has to be altered in some kind of way in order to get it to do what it's going to do. So when we burn something, we're changing the substance from whatever it was before to whatever it's going to be after. Usually carbon dioxide and water, but there are other kinds of combustion reactions that exist as well. And what we will always see out of a chemical change is that the substances that we start with end up being different from the substances that we end with. And that's what separates the chemical change from the physical. In a physical change, we have the exact same stuff at the beginning as we do at the end. It might just look a little bit different. But the before and after for a chemical change, they're not the same thing at all. Oftentimes, what that means is that the resulting products after a chemical change will also have different properties, different physical properties, sometimes different chemical properties as well. I burn this piece of paper and it gives me carbon dioxide and water. Now, this paper is highly flammable. Carbon dioxide and water, neither of them are flammable. So not only have we changed the physical properties, going from a white piece of paper to two colorless gases, but we've also changed the chemical properties as well. Flammability before, non-flammability after. And so here's just some examples of chemical changes to go along with that. All right, let's kind of review where we are. I've got 5 properties here. Let's see if we can identify them as either physical properties or chemical properties. Ice melting in the sun. Physical. The ice isn't changing in any way other than just how it looks. Copper is a shiny metal. Also physical. We're just describing how it looks. Paper can burn. Chemical. It's describing a reaction. A silver knife can tarnish. Also chemical. Tarnish is a reaction between metal and the sulfur in the air. A magnet moves iron particles from a mixture. All right, this one's tougher, but it is physical. When you're moving that magnet around, you aren't changing the iron into anything else. You're just using a property of the iron, its magnetism, to separate the components from each other. Right? Yes. It would change the mixture, but remember, mixtures are physical combinations. So when we change a mixture, it's still not a chemical change. If you boil off the water and leave behind the sugar, yes, you've done a change, but it's a physical change. The water in the mixture is water before and water after. The sugar in the mixture was sugar before and sugar after. It looks different, but chemically it's the same. And that's why it's physical. Other questions? All right, let's look at changes. Physical versus chemical changes. I burn a candle. Chemical. Remember, burning processes are going to change the substances. All combustion is a chemical reaction. Ice melting on the street. Physical. Toasting a marshmallow. Chemical. You're turning that sucrose into other substances. Cutting a pizza. Physical. Iron rusting on an old car. Chemical. All right. All right, any last questions about physical and chemical change?
I know that bright things is making a chemical change, but in my mind, I'm like, okay, it's just melted candle wax. You can still make it, remake a candle out of it.
Okay, well, how would you remake the candle?
Melt it.
Okay, but if a candle melting is the only thing that was taking place, why is it that a candle gets smaller as we burn it? It's not just evaporation. 'Cause that would mean that it's just turning into a gas. Right, so what's happening is the heat of the flame is causing the paraffin, the wax, to vaporize. But as it vaporizes, it's also combusting. It's combining with the oxygen in the air and turning into carbon dioxide and water. And that's why we can't recapture it and just recreate a candle again. Once it burns, it's completely gone. It's turned into gases, it's turned into something else. We can't reconstitute that. Otherwise, we would never have to buy more than 1 or 2 candles in our lifetime. Because all we would do is light it, let it burn, cool it down. It would come back to be, put a cap on it. It would reform. And then we could just light it again and again and again. And we'd only have a little bit of loss, to evaporation or something like that along the way. It has to be a chemical process. Otherwise, we wouldn't see that. We lose over time. All right, other questions?